Hi everyone. Today I'll be presenting on Sarita Rosenstock, Justin Bruner, and our own Kaylin O'Connor's 2017 paper in Epistemic Networks, Is Less Really More? And so the main findings of this paper are the following. So in two papers, Zollman uses a network epistemology model to argue that less communication between agents in the network might actually be beneficial for the epistemic community. And this is the case even though less connected networks, i.e. those that have less communication between the agents, might actually slow down the speed of conversions to this consensus. In this paper, however, Rosenstock et al. Show that Zollman's results only hold under certain very restrictive conditions, namely when learning is especially difficult. And we'll go over what especially difficult means in this context. But a conclusion we might draw from this paper is that, in most cases, less connectedness, so less communication, actually really just slows the arrival at a consensus without providing any real epistemic benefits. And similarly, the authors also show that related results from Kummerfeld and Zollman in 2016 are also sensitive to certain parameters, and so they're not so robust. So here is the outline for my presentation. I will first go over Zollman's 2007 results, leaving the 2010 paper to Syra, which we had to read for today. And then I will show Rosenstock et al.'s expansion of this model, namely considering the model by tweaking some parameters and showing that the results aren't robust. And I'll do the same thing with Kummerfeld and Zollman's, present it, and then look at Rosenstock et al.'s expansion of this. So in his 2007 paper, Zollman's model follows closely Balin-Goyal's, who consider the general conditions under which a network of learning agents will adopt the same beliefs. So this is a motivating example. We have a group of clinicians who use a certain drug, A, with a known success rate to treat a disease. And recently, drug B has come to the market with an unknown success rate. And the question then becomes, will the group of clinicians converge in their consensus to which drug is better, and will they converge to the drug that is actually better? And so each clinician has some belief as to which of the drugs is more successful based on previous experience with drug A and the new data on drug B. Then the clinicians prescribe the drug they prefer, all while noting the success rates of the other drug. Then the clinicians communicate with each other and their success rate. So note that here the clinicians both learn from their own choices and from their neighbors. So let's quickly see how a toy example of how this model might work. So here we have 4 clinicians, and each assigns a certain credence to how the drug will work, and so how likely the drug will work. So here they all have the credence of 0.5, presumably on good evidence that drug A works 50% of the time. But then we have drug B, and so they assign a certain probability to it. Some people think that drug B is more likely to be effective, others don't. And so we assign 0.5 plus or minus a phi, where the phi can be any number between 0 and 0.5. So here, the top and the left clinicians think that drug B is more likely to be successful, while the right and bottom one think that drug A is more likely to be successful. So in the model, then they choose which drug to prescribe at each round based on which drug they assign the highest credence to. So here, the top and the left clinicians will assign at least in the first hand, will assign drug B, while the right and bottom clinician will assign drug A to their patients to treat the disease. Whether you think this is, I think it's a question of whether this is a good model, because one might think that you could have a degree of belief of 0.5 that a drug will work, and a degree of belief of 0.7 that another will work, and maybe give drug B sometimes and drug A sometimes. But maybe we can discuss this more in class. So in the network, each clinician prescribes the chosen drug n times in a round, and in Zollman's network, it's 1,000. Then their payoffs come from a binomial distribution, and one way to visualize this, if you're not familiar, is suppose that the actual success rate of the drug is 0.65, so the drug works 65% of the time. Then for each prescription, the clinicians get payoff 1 with probability 0.65. So here, what I write is not exactly correct. That the payoffs will be 650 for the ones that assign B and 500 for those that assign A, because it's from a normal distribution. But this is just to visualize. But the ones that assign drug B might actually have a lower payoff given the probabilities than someone who assigned drug A. Though it's less likely, but it's still possible, and might lead the community or that person to error. Then in the network, the agents, i.e. the clinicians, are connected in some way, and they are Bayesian agents. So this, I think, should at least give an intuitive feel for the model, and we can go to the central result of Zollman, namely that a sparser network structure can actually benefit an epistemic community. So what does this mean? It means that a complete network, the one on the left here, might converge faster, but his results show that they are less accurate. And as you decrease the number of nodes between the agents, the number of edges between the nodes, you might get a slower convergence, but you'll actually be more accurate. And this seems as a surprising find, and Rosenstock et al. Call this the Zollman effect. So then after this maybe unintuitive finding, the Rosenstock asked, okay, what epistemic role do these models actually have? So how seriously should we take these results to inform real-world communities? Should we go around telling scientists that they should communicate less with each other because they will then arrive at some truth with a higher likelihood? Well, let's first look at what kind of story this model gives us. So the authors say that this model gives us actually a how potentially story, and not a how possibly. A how possibly story of modeling is, for example, Quine argued that linguistic meaning can't arise unless you have already some established convention. However, if you're familiar with the work of Brian Skirms and his work on the evolution of signaling, Brian actually shows that it is possible to arrive at meaning without any convention on the meaning of the terms. So, however, this model clearly also, well, perhaps not clearly, but also doesn't seem to track the real world or real epistemic communities super well, or at least this unintuitive feel we have might tell us that. And so Rosenstock and all argue that it provides us a sort of how potentially story. So potentially epistemic communities might benefit from a decreased connectivity in certain cases. And so back to the question, so how seriously should we take the results? One big factor might be, okay, how robust are the results of this network? And here's a nice quote: highly robust phenomena are more likely to have applicability to the real world because the conditions under which they occur are more likely to hold. And again, we might also discuss in class, is this really the case? Are models that are more robust under parameter changes actually more likely to track the real world and how it is? And this might be the case, but it also might not. So maybe we can discuss this. But now they ask, rightly, are Zollman's results robust? And this is a question that the paper essentially answers in the negative. And so the authors evaluate Zollman's model through 3 different parameters, namely the success rate of the new drug, the number of trials per round, and the population size of the network. And they find that Zollman's results are not robust under any of these parameter changes. So let's look at the first parameter tweak, you might call it, which is the success rate of the new drug. It's worth noting that in the Zollman papers, the probability of the success of drug A is of 0.5, and the probability of the success of drug B is 0.501, which, I mean, as you can see, they're quite close to each other, and they vary in their success rate by less than 1%, namely 0.1%. And what Rosenstock et al. Show is that increasing the probability of the success rate of the drug by even a small amount results in the Zollman effect vanishing. But it doesn't reverse, so it's never the case that the complete network actually does better. So let's look at the simulations that they run. So on the y-axis, you see that the rate of convergence, and on the x-axis, you see the different values of the success rate of the drug. Note that in these simulations, the values of the population size is 10, and the value of the number of trials per round is 1,000, and these are the same as in Zollman. So this is Zollman's model ran with the only difference being the probability of the success rate of the drug. And what's surprising is that if you even get the success rate of the drug being 0.502, the Zollman effect really almost vanishes, and 0.504, it completely vanishes. So really, by tweaking it by only a few percentages makes the effect completely disappear. And an intuitive explanation for this result is that 0.5 and 0.501 are very close to each other, and by making the success rate of the 2 drugs more different to each other, then the agents will have an easier time distinguishing between the effectiveness of the 2 drugs. So it might be very difficult to distinguish which drug is better when one has a 0.501 success rate and one has a 0.5 success rate, but easier when their success rates are different. So what are some takeaways from this? Is that Zollman seems to claim that this Zollman effect occurs for a wide variety of parameter values, but however, for most, maybe even relevant portions of the parameter space, this effect essentially disappears. However, decreasing the connectedness still slows down the learning. So it seems like we get no benefit from taking away the connectedness while still getting the negative effects from it. But again, the Zollman effect never reverses, so it's never the case that the complete network does strictly better than the cycle network. So the next parameter change that the authors look at is by changing n, namely the number of trials per round. And they find that by increasing the number of trials per round, the Zollman effect is actually inversely related to it. So the more trials per round, then the least we see the Zollman effect. Again, we see it here on the table on the right. On the y-axis, you have the rate of convergence, and on the x-axis, you have the number of trials per round. And this makes sense because then the agents have more data to go through, and so they will presumably do better with the more data that they have. And so in this model, the population size is still 10, but the probability of the success rate of B is 0.51. And maybe one question to Kaylin would be, would the Zollman effect disappear if the success rate of the drug was still the low value of Zollman's original paper? And now we move on to the third tweak, and this is when they vary the number of agents in the network. So they look at, remember that Zollman actually looked at networks of size 3 to 10, and now Rosenstock et al. Looked for population sizes of 20, 40, 60, 80, and 100, while keeping the very low probability of the success rate of drug B and the same amount of trials per round. And again, we see that in larger populations, the Zollman effect again decreases. Even though there's still some, it's perhaps not even significant, given that once a population size is at 20, the complete network converges with a rate of 95%. Furthermore, the cycle network again converges way slower, especially when the population size increases. So here we can see that in a network with 100 agents, the complete network converges at 99.12% in 20 rounds, while the cycle does converge at 100%. It does so in 1,977 rounds. So these sparse networks really learn much more slowly, and it might not be worth the risk. That the risk might actually be worth the slowness of the cycle network. Yeah. So just to drive the point home, as they say, they mapped the Zollman effect as a function of the population size and the probability of the success rate of the new drug. And here, really, we see that the Zollman effect only happens when the probability of the success rate of B is very low and the population size is very low. If you increase any of these parameters independently or both, then you get this Zollman effect that disappears. So, having seen this, we'll briefly turn to Kummerfield and Zollman's paper, and the authors don't treat this one as extensively as the other two Zollman models, but they still tweak some parameters and show that these aren't robust. So what do Kummerfield and Zollman find in their model? They find that when agents have exploratory tendency, then actually the complete networks are more successful than cycle networks. And so this might be considered a reverse Zollman effect, because remember, the Zollman effect is that cycles perform better than the complete networks. And they consider a complete and cycle networks of 8 agents, and the agents are not Bayesian updaters, but rather this thing called epsilon greedy, where an epsilon greedy agent updates on the basis of observation of agents she's connected to, which action has had the highest average payoff in the past, and takes this action with probably 1 minus epsilon and tries the other action, which is this exploring tendency, with a probability epsilon. And again, the model is a bit different because the payoffs aren't exactly the same as before. Namely, the worst action gets 0. Remember, in the other one, it would be a binomial distribution, and if they picked the worst drug, namely drug A, they would still get a payoff of 1 in each time with a probability of 1/2, but here they just get 0. And they find that the better action yields an outcome. No, so the better action yields an outcome drawn from a normal distribution centered at a value greater than 0. Now, one question I had for the class would be, why do they say that this is the riskier action? I was a bit puzzled by it, but anyway. They find under this model that the agents, as agents explore more on their own, then connectivity becomes actually beneficial to inquiry. So for low epsilon, then cycles are more successful, meaning that the payoff on average over all rounds is higher. But as epsilon, remember this exploratory tendency, increases, then the complete networks start outperforming the cycles. And now we ask the same question again that we did with Zollman's, is the model robust? And so Rosenstock et al. Consider the models with different payoff distributions and with different standard deviations in this payoff distribution. Namely, with the mean of the payoff distribution being 1, 2, 3, 4, and the standard deviation of 3 and 9. And they looked at 2 different agents, namely an epsilon with an epsilon of 0.35, so this is quite an exploratory agent, and an agent of 0.05, so maybe a more conservative agent. And again, they find that their findings are not robust under these parameter changes. So as the mean of the payoff distribution is increased, then the network effects on the performance is decreased for both epsilons, and decreasing the standard deviation of distribution also decreases the network effects. So here we see that on the x-axis, we have the mean of payoff distribution from 1 to 4, and the difference in success between the cycle and the complete network. And we see that as you go to the right on the x-axis, i.e. as the mean of the payoff distribution increases, then the success rates of the networks becomes very close to each other. And similarly, when the standard deviation decreases, then the network, the difference in success between the network also decreases. So some takeaways from this discussion is that, okay, the effects of connectivity disappear when other parameter values are considered, and again, when agents have an easier time determining the better action, then the structure becomes less important. And this was also the case looking at the Zollman models. So here's a brief summary of the network results. Namely, Rosenstock et al. Find that Zollman's model and Kummerfold and Zollman's model are not robust under parameter changes. And the lesson we might draw is that network structure matters more when inquiry is trickier. And again, we've seen what this means. But when the data is actually good enough, then decreasing the connectivity only slows down the learning process and doesn't give any epistemic benefits. And so now we can ask this question again. So should we take, how seriously should we take the Zollman model? Should we take the potential for decreased connectivity to improve epistemic community outcomes seriously? Well, after looking at this paper, maybe, but only in certain very specific types of epistemic community, and namely where learning is more difficult. But even in these cases, Rosenstock et al. Suggests that they still think that there are better solutions to getting networks to converge. Maybe, for example, having standards for the amount of data to confirm or deny a theory, and having more exploratory agents. And maybe if someone in the class has some suggestions as to how to do this, I'd be happy to hear it. But a conclusion from their paper we can see is in the following quote: our results should decrease confidence that epistemic network effects of the sort observed in these models regularly happen in real-world communities. Namely, they don't have the confidence that they happen should be decreased because the results aren't very robust. And they say, we cannot say with confidence that we expect real-world epistemic communities to generally fall under the area of parameter space where the Zollman effect occurs. And they emphasize that because of the sensitivity of network effects to structural changes, we should really be cautious of our application in these models to real-world epistemic communities. And that was my presentation. I think it would be nice to think about how important is robustness for these models, and should we take now this expanded model by Sarita et al. To give us some confidence that actually connected epistemic communities do fare better in the real world.